Thank you everybody for being here and for hearing me out. So yeah, as Frank explained, I'm Tim, and today I would like to tell something about how we started out as a design company, design office, making furniture, and we kind of made our way into the 3D printing world and ultimately came up with an idea to print a bridge. But before I start, I want to show you a video that every time I see this video, it really inspires me, and it kind of tells us as a company that everything's possible. Everything you want to do, if you put enough time and effort in it, you can do it. So.
Ja, her har vi togskinnene og de tekniske tegningene, og Martin som begynner å bli ferdig med midget. Det er bra.
It appears to be not working. Maybe my computer went to sleep mode, I don't know. Ah. Okay, let's try again. Ah, there it is. But now no sound. Wait. Everything's possible, yeah, exactly. No, it's up. Strange. Sorry about that. Let's see.
Ja, her har vi togskinnene og de tekniske tegningene, og Martin som begynner å bli ferdig med midget. Det er bra. Ja.
Har du nok batterier til togkammer?
Ja, det er masse ekstra batterier også.
Henrik! Kjapp deg ned, vi må ut!
Kjapp deg, Henrik. Yes, ass! Yes! Dritbra! Yes, ass! Det er nydelig! Det er dritbra!
That's a cool video, huh? So yeah, I mean, of course it's a fake viral video and all, but it really shows that you put your mind to it and you can do something. And it's always intrigued me that if you have, since I was young, when I saw someone with a welding machine and an angle grinder and they built something, and I was really, intrigued by welding itself. You can make anything, just a bunch of steel, angle grinder, welder, and you can build anything. And these techniques have been around since the Industrial Revolution more than 100 years ago. But right now, the interesting thing is that we are in a new industrial revolution, and one that's more fed by information and by access to information. Everybody can pick information from the internet, do stuff with it, improve on it, build it, post it back, and the learning curve is really steep in the last 10 years, last 20 years, but it's going steeper and steeper. For instance, this is a guy, and he has a son, and his son was born without the fingers on one hand, and he wanted to buy a prosthetic hand for this guy, for his son. But it was way too expensive, of course, so he decided to start developing it himself, and he went online, he looked for photos, he looked for CAD files, and he just printed one for, instead of $10,000, he printed one for like $15 worth of plastic, which is, quite amazing if you think of it. And another example of how the development is becoming more democratic is this guy. It looks like a really, childish website, but it's a guy who actually wants to open up space travel. He was like, why could only NASA and big countries and big companies go to space? Well, why can't we do it ourselves? So he opened a website where he shows tips of how you can go to space, how you can put your own satellite in space and such, which I think is really interesting. So a little bit about what we do. We started out as a furniture company led by Joris Laman. He's a renowned Dutch designer. And we make high-end furniture, really experimental furniture that we sell throughout the world through our gallery in New York. And we use a lot of high-tech production methods, high-tech materials, and a lot of 3D printing. First, we only used it as a method of making something, but then as 3D printing advanced, we decided to make complete furniture with it. And one of the examples of the things we do is the bone chair. This is a chair from 2006, and it's based on how evolution would design a chair. So to explain a little bit better, the guy you're seeing there looks a little bit like Ozzy Osbourne, or a little bit like, I don't know, but he's a really smart scientist, Klaus Matek, and he spent his whole life investigating, researching how trees grow and how bones grow. And he found out that trees have a capability, the capacity of grow material where it's needed. So if there's a wind from the west, it'll grow material on the east, for instance. And together with Opel, they decided to put that in a software package, topology optimization software. So the idea is quite simple. You have a basic design space. You put forces on it that you would expect on a part, and then the computer starts calculating until it breaks. And right before that point, right before it breaks, is the most efficient shape of the form. And in our case, a chair. So here's a quick animation of how we did that. We took a basic design space, put forces on it, force on the seat, on the backrest, you know, wiggle forces because you're never sitting still on a chair. And then in the end, something like this comes out. But of course, this is a rendering, and you can't sell a rendering. So we had to produce this into something, you know, that we could sell, that we could make, a chair. And this is actually where, for the first time, 3D printing came into our work. On the left, you can see a mold in which we cast a chair in aluminium, and the whole mold is 3D printed in kind of like a plaster material, sand material. So instead of making a mold traditionally, we 3D printed. And another example is these chairs. It's from the same series, also the bone chair series. It's a little bit different material. It's polyester resin mixed with marble powder. And we had to make this chair ourselves because we went to different producers, and everybody said either it's not possible, or you're crazy, or it's way too expensive, or we didn't trust them, or whatever. So we decided to do it ourselves. So what we did was we 3D printed actually the mold of this chair as well. It's a mold that's, on the right you can see the exploded view of the mold. It exists of about, I think, 75 to 80 pieces, which we all screw together and then cast the resin in. But this is just using 3D printing only for the mold and as a to make tools, so to say, and not to make the final product. And the problem with that, with making big things and useful things, is what you see here. I think 95% of everything that's 3D printed on the internet is iPhone cases. I bet there's more iPhone cases than iPhones in the world. And so it's all, you know, it's plastic material, it's small, it's kind of crappy, people don't know what to do with it. They buy a printer, but they don't know what to do with it. But 3D printing is kind of like the magic word. It should be 3D printing, right? If you hear 3D printing, you think it must be good. But then I kind of like these examples of 3D printing. I mean, a pancake, 3D printing a pancake. If something's flat, then it's a pancake, right? And the same goes for makeup and pizzas. It's cool projects, very cool. I would really love a 3D pancake printer, but it doesn't really have anything to do with 3D printing. So the current status of 3D printing, especially of the consumer-grade 3D printers. The prices have dropped really dramatically. But what we as furniture designers would like to see is that the building volumes go up. You know, and another line, a blue line or a green line in this graph, building volumes going up, materials, choice of materials, durability of materials, everything, and more lines. But that's not the case yet. I think the 3D printing is now in a stage of the dot matrix printer in the 80s. You know, it's slow, only one material at the same time. It's cool, but there's a lot of work to be done. But we decided to use it anyway. I mean, there's two things you can do: complain about it or do something about it. And we decided to do both, basically. We still complain a lot about it, but we also decided to use the shortcomings of the small printers to print something, to make something that we could actually use. So we decided to divide a chair into actual puzzle pieces and print each puzzle piece on a 3D printer, on an Ultimator printer. And after that you assemble all the pieces together and you have a full chair. And this chair actually we have placed it online for free download. So everybody who has a 3D printer can download it and print it themselves. You need a little bit of patience because the printers are not really fast and it's a lot of work. It takes like 2 months to print or something with the printers you have now. But it's like a 35 euros worth of material. I mean, that's even IKEA can't compete with that. So, I mean, the future of 3D printing is going to be bright and big. And the future of 3D printing, this is a project we did for the High Museum of Art in Atlanta. They asked us to look into the future of 3D printing, how we thought 3D printing and materials would evolve. And we looked into these self-assembling materials, self-programmable materials, so you don't need a printer anymore almost. You program something, you want a chair, you program a chair. If you're sick of the chair and you want a table, you program the table. And then it self-assembles itself into a table. Of course, this is all into the future. These cubes you see, they are done by Cornell University and MIT. They're about this big. And they're working on cubes like this big. But if you would scale it down, you know, with a graph like this, then at a certain point you actually get a material and something that really, you know, looks like and feels like a material. So what we did was we programmed a robot. That was our first acquaintance with robotics, to pick cubes, steel cubes, and place them together to kind of produce a table. And this was really slow. I mean, it took months probably to finish this table, but it wasn't about efficiency. It was about showing what it could be in a later stage. And we made a few tables of these. The design of the tables, we deliberately took a really decorated shape of it, a really decorated form language, to be able to show that the smaller the cubes are and the smaller the molecules are, the more it looks like material and the more it shows you detail. And so as you can see, the table on the right has 1.2 million blocks. Actually, those were all assembled by hand because we didn't have time to program the robot to do it. So it took some interns and freelancers a long time. It was like a 3-month project, so we were kind of stuck on that. And one other interesting thing before we skip to the bridge part is it's also interesting to show. We also wanted to see what you can do with only one material per chair or per. How can you change the properties of the material in such a way that they get different properties? And we have this series of chairs. These are just sketches, microstructures, chairs, and we kind of broke down the material properties almost to a molecular level, and to see how we can design a chair where all the properties are in the right place and in the right where they should be. For instance, this is 3D printed out of thermoplastic polyurethane, which is a really flexible material. And we designed the chair in such a way that in the places where you need strength, it's thicker, you know, more material. In the places where it's flexible, it's thinner, so you get soft seat. With this chair, it was kind of like a little bit the same, but also different. Here, where you need strength, the material is more full, and where you need lightness, the material is more open, so to say. But problem with these chairs, all these chairs, we made 3 in total, is that we had to print it in different parts. You can see many different parts. So there's the building block of where we print this chair in. It's printed in full aluminium. It's about this big, and the chair is like this big. So we needed 25 parts to do this, which is kind of irritating if you want to print it in one piece. can understand. And another downside was the support structures you need. For almost all the printing techniques, except laser sintering, you need a lot of support structure, which afterwards you have to cut away. And all these irritations combined, we thought, okay, if nobody's going to make a big printer where we can print full-size furniture, then we're going to do it ourselves. So we started the MX3D program. We combined a robot with 6 axes with different printing end effectors. So we could, if once you program the robot, you can put every tool on it and it starts printing or in any material, whatever you want. And the good thing about doing it like this, the main thing about doing it like this is that with traditional printing techniques, almost all of them, they are all bound to a bounding box. So you print on a surface and then afterwards you have to take it off and put it somewhere. And if you print with a 6-axis robot, you don't have to print here, you can also print there, or you can start anywhere. And once we were thinking about it, we were thinking about, yeah, you know, what can we do with it? What can we use it for? So the first printer we developed was the MX3D Resin Printer, which prints a 2-component urethane resin, really fast curing. So this video is speed up a little bit, I think like 3 times. But we found out that we could actually print horizontal lines starting from a wall. So you're basically printing in midair. And it's in the 2 cassettes. There's A and B components mixed together. Apply some heat, and it instantly cures really fast. So we were really interested by what we could do with this. But also, this material had some downsides because it's you know, it doesn't really look nice. So it's again not something you could sell as furniture. It's not really strong, but it was a good start for us. So from there on, we decided to look further and see if we could use more materials, different materials, which brought us to the MX3D metal printer. And this is a printer that we can print stainless steel, aluminium, basically all the materials you can weld. Theoretically, you could print with this machine. And the idea is very simple. A robot and a welding machine combined together, program some software, a lot of software actually, and then before you know it, you can print. But I mean, these are the first results we printed, so it didn't really work from the beginning. But I mean, we kept on testing and testing, and you know, before long the lines got better, and we could actually print stuff with it, which really got us actually really excited. And this video shows a little bit the process, also speed up, because for this video we actually had to sit inside the room for days to make a photo after every welding dot that the machine did. So to explain it a little bit, the welding machine is placing a drop of molten metal on top of another drop of molten metal, and then, you know, like that, the material grows by itself almost. And so we looked at different strategies for printing. And one was the FDM strategy, the tubes you can see on the right. That's basically the strategy all 3D printers use. So you make lines and on top of each other, and then the material grows, so layer for layer. But the 2 on the left side, you can make structures and lines as well. So we can make really thin lines with all dots and combine them together to make really big structures. So the first thing we actually made with it was also an art piece. This one now is in the High Museum of Art in Atlanta. And we made a few other ones now. We're working for one on a museum in Groningen in the Netherlands as an art piece. But then we thought, what else can we do with it? I mean, this is just an art piece, but we want to see, you know, there's really big implications for a technique like this. You can print, literally print outside the box. You can make structures. You can go further than just furniture. So we were thinking about making ships, making shipping propellers, making structures, maybe, you know, concrete reinforcement, stuff like that. But that we really wanted to do a project that we could show everything about this technique, everything the technique could do. And we are from Amsterdam. If you image Google Amsterdam, this is what you see, canals and water. And, well, depends on if you have your safe search on and off, but you could get different results, but this is my computer. So, I mean water, canals. And so, I mean, it was quite obvious for us we have to make a bridge, because it's really symbolic, a bridge in an old city as Amsterdam, showing the new technique and the new possibilities of this technique. So we went online with this video about 2 months back. Speed.
At first, they were little worm-like blobs. It was hard to see, but we saw a universe of possibilities. Of course, many things went wrong. A welding machine exploded, nozzles got stuck, and the robot got disoriented. But then, they became long lines, complex curves, and double-curved oval tubes. It was like drawing in mid-air. And after endless testing, we were able to speed up the process and produce this complex sculpture of lines. And now, we are ready for the ultimate poster project, to test all facets of this highly promising printing technology. A large-scale object that is functional and meaningful. We are going to print a steel bridge in Amsterdam.
So when that was out in the open, we really had to, you know, because it got a huge amount of attention, and so now we actually have to print a bridge, which we are really excited about it, of course, but it's not going to be an easy task. And the idea is to have two robots, as you could see in the animation, work their way over the canal. It depends a little bit on the location where we're going to print it, if that's going to work, actually print it live, but otherwise we're going to print it live in our test facility. One of the locations we really want to have the bridge is the red light district in Amsterdam, for other reasons than you might expect. But the most narrow canal of Amsterdam is in the red light district. So we thought if we better start small rather than really big, so we can always do bigger bridges afterwards. And plus, there's a lot of tourists there. It's a really busy area. It's the oldest area of the city, so perfect for a bridge like this, we think. So we hope Amsterdam city is also thinking the same, which is going quite well. But the problem is that it's really, really busy there. So for live printing, we don't know if that's going to work. We need 24/7 security and stuff like that. So what we're going to do now, next step, is we are opening our test facility in the Amsterdam north part of Amsterdam, in an old shipping wharf, a really nice location. And we're going to do a full test bridge there. And this is a little bit what it's going to look like. We open it up October 8th. And after that, it's open for public. People can come and see what we're doing. So we really actually want to keep the whole process open and for people to see. And just a little bit more about the design. The good thing about printing, actually 3D printing a bridge, is you could go completely crazy with the shape. You know, the 3D printing for a printer, it doesn't matter if it's straight lines or if it's curved lines or if it's decorations. I mean, in the last decades, decoration has kind of been cut back from architecture because it's too expensive. It's too expensive to have a lot of people with chisels and hammers making decorations. But with 3D printing, you can actually decorate again, and we think that's really interesting. These are just wild ideas. You know, the whole design process, we are still working on it. We're going to test now for about 1 year. I think there's 8 months left now of testing. And then after that, we're going to decide, when we completely know what the technique can do, then we're going to decide what the bridge is going to look like, because it doesn't make sense to make the same design as other bridges, because then it's a lot cheaper to make another bridge. But these are kind of ideas about, you know, also what you could see in the beginning, putting forces on a design space and letting the computer calculate it. So the only question remaining is, why would you 3D print a bridge? Why would you do a project like this? And for us, the main answer is because we really want to do it. It's a cool project. We love getting into something completely crazy and impossible, as some people say. That's the main reason. And the other reasons, if you look back at the beginning of the presentation, by doing stuff like that, you develop, and you never know in advance what comes out of it. You have to see what comes out of it. You have to first do it, and then you see what we learn, how much we learn, and if it's any good. So I want to leave you with the last short film that kind of explains about how fast development goes, and sometimes you don't know how important things can be.
Heeft u een mobiele telefoon?
Nee.
Waarom niet?
Nou, dat heb ik niet nodig, want ik word toch niet gebeld of zo.
Heeft u een mobiele telefoon?
Nee hoor, heb ik niet.
Waarom heeft u er geen?
Nou, ik zie er niet van in.
Dan ben je aan het fietsen en dan word je gebeld.
Vindt u het belangrijk om altijd bereikbaar te zijn?
Ook niet. Ik ben niet zo belangrijk.
Ik heb gewoon een telefoon, waarvoor moet ik een mobiel hebben?
Dat is handig. Maar als ik ergens strand, dan is er ook altijd ergens wel een telefooncel of een boerderij met een boer met een telefoon.
Ik heb al een antwoordapparaat, dus thuis ben ik altijd al bereikbaar. Of dien dan terug te bellen als er is gebeld, maar ook nog eens onderweg. Als ik in de trein zit of in de auto gebeld worden of zelf kunnen bellen, vind ik niet nodig.
Het lijkt me helemaal niet leuk om altijd bereikbaar te zijn.
Ik ben student en ik heb een antwoordapparaat en dat is prima.
We hebben het jaren zo gedaan en ik vind het wel goed zo.
Ik heb een buzzertje voor hoognodige problemen, denk ik. Maar ik hoef niet continu zo'n piepding op een terrasje te hebben en zo.
Als mensen mij bereiken willen, dan kunnen ze dat met een brief doen. En is het dringend, dan ben ik telefonisch thuis te bereiken.
Ja, ik weet nu al dat ik hem overal laat liggen. Ik laat hem vallen. Ik ben ook gelukkig zonder.
So that's an interview of 15 years ago, eh? And then it says 2005, but it's 1999, only 15 years ago. So that's how fast things go. I myself was one of those people 15 years ago. But thanks a lot. If you have any questions, please feel free to ask.